So basically, let me say a little bit about what I'm going to do. So there are 5 lectures, and it's supposed to start off relatively elementary for the students in the audience. Unfortunately, as I look at the audience, I see very few students. So this will be a little too elementary for many of you, and for that, I apologize, but I'll get you later, so we'll be even. So basically what I want to do is I want to talk about some results on minimal surfaces and mean curvature flow. The original results I will talk about are all joint with Toby Colding at MIT. I want to build there a little bit slowly. So we're going to think of minimal surfaces as critical points for the area functional, and then so in other words, the mean curvature is the gradient of the area functional, and then you can look at an associated gradient flow, the mean curvature flow. So we'll try to interpret things from that point of view. The results for minimal surfaces will essentially exclusively be about 2-dimensional minimal surfaces in R3. Then when we do the mean curvature flow, it will be in all dimensions for hypersurfaces. There, we want to sort of understand some dynamical questions about minimal surfaces. So about mean curvature flows. So these mean curvature flows have singularities. Some of these are dynamically stable, and some are not. So stable, I mean stable under perturbation, and that's the question we're going to try to that we will answer. Okay, so without further ado, for today's talk. So again, as I said, the mean curvature is the gradient of the area functional. So we have the critical points, which are minimal surfaces, and then the flow, which is the mean curvature flow. This is a gradient flow, which is a steep descent. It's the fastest way to reduce the area. So first we'll warm up by considering analogous problems in simpler settings. The first is, instead of looking at the area, we look at just the energy of a function. I'll talk about that first. In that case, the critical points are harmonic functions, and the gradient flow is the heat equation. Then we'll bump it up a little bit, and now we'll talk about the energy of a curve, energy or length of a curve. And so there, the critical points are geodesics, and the flow is the curve shortening flow. So we'll warm up with those results, and then in the next lecture, we'll move on to area and minimal surfaces, and then to see. Right. Now all I have to do is figure out how to advance the page. There we go. Right, and then from that to, okay, well, yeah. So how do I advance the page? Arrows. Thank you. Perfect. Okay. So right. Okay. So what's a harmonic function? So harmonic functions are solutions of the Laplace equation. So here, just to set the notation, just to remind you what the Laplace equation is. It's the trace of the Hessian, or the sums of the diagonal second derivatives. So that's mostly to set the sign. Some people would tell you the Laplacian has the opposite sign, which makes it a positive operator. We'll make it, or non-negative operator. We'll make it a non-negative operator by leaving this sign, but then declaring an eigenvalue to be a solution of Laplacian u is equal to minus lambda u. Okay, so now these arise as critical points of the energy. Here, just to remind you again, here's the energy of the function. The factor a half is non-standard, but in order to make the heat equation a gradient flow instead of a multiple of the gradient flow, we'll put this factor a half in here. So now, suppose that I have a 1-parameter family of functions. So I think of u plus t times a function phi. And now if I look at the energy as a function of t, so I think of u as a fixed function, the function phi vanishes on the boundary, so it's some compactly supported perturbation of u. So I just expand what the energy is, and I differentiate it, and at t equals 0, I see the derivative is given by, right, so the derivative of the energy at t equals 0, is in theory somewhere, is given by the grad u dot grad phi. And now we apply the divergence theorem, take the derivative off of the phi, and it's minus phi times Laplacian of u. So from this point of view, thinking of phi as being, phi is the tangent to this, so this is a path in the space of functions. The function phi is the tangent vector to that path. And so this means that the gradient of the energy functional is the Laplacian of u. So the critical points, so the ones where no matter what phi, okay, so now it's a critical point where this derivative is 0 no matter what phi is. And so that means that the integral of Laplacian u against any phi has to be 0. So in other words, Laplacian of u has to be 0. So we see that the critical points are the harmonic functions, the solutions of the Laplace equation. So in fact, harmonic functions are not just critical points. They are minimizers for the energy. So here, let me just remind you of how you would see that. By the way, of course, just looking at this equation, if you imagine what the second derivative is, if I were to take a second derivative, I would just get grad phi squared there. So the second derivative is positive, so it passes the second derivative test. So we think of them as local minima. But in fact, you can say more. They are global minima. So here, now Laplacian of u is 0, and I take a function in a domain, bounded domain, and I take a function that's 0 on the boundary. So just by the divergence theorem, if I take the divergence of phi grad u, then I would get a Laplace u, which drops out, and a grad phi dot grad u. So this means that no matter what phi I stick in there, as long as it's 0 in the boundary, its gradient is L2 orthogonal to the gradient of u. So now let me expand out the energy again. So here I think of u as being harmonic, or I mean u is harmonic, and I expand out the energy of u plus some function phi. So when I expand that out, the cross term drops out because grad phi is perpendicular to grad u no matter what phi is. So all I get are the two squares. So from this equation, you see the energy is minimized when phi is 0, and that's the unique minimum. So this shows that this, a silly argument just shows that harmonic functions globally minimize energy in a very strong sense. This is like a convexity of the energy functional. All critical points are minima. Okay, so now we'd like to introduce a little bit of dynamics to this. So now suppose that I start with a function. It's not necessarily harmonic. So harmonics are the harmonic ones are the minimizers to the energy. I'd like to improve the energy as efficiently as possible. So since the Laplacian, or minus the Laplacian, is the gradient of the energy, that tells me the direction of steepest descent. That's the most efficient way to move. So I'd like to improve the function by moving in the direction of Laplacian of u. So I solve this heat equation. The partial derivative of u with respect to time is equal to Laplacian of u. This is the ordinary heat equation on Rn. And then when I do this, I now evaluate what happens to the energy. So we saw the first equality. That's true no matter what the function u is. And then in the second equality, we plug in that the partial derivative of u with respect to time is just the Laplacian, so you get this negative term. So this means that under the heat equation, the energy is always decreasing unless you're already at a harmonic function. So harmonic functions are fixed points of this flow. So I think of the space of functions, and then there's the energy functional, and this is a negative gradient flow on that space of functions. Okay, so energy decreases along the flow, except if you're literally at a harmonic function, and those are fixed points for the flow. Those are called static solutions. Okay, so that's now one more comment. We'd like to understand just a remark about gradient flows. So suppose that you have a function, and now so the energy function is a function on the infinite dimensional space of functions. So let's just go back to consider functions on R2. It's a little bit simpler. And let me ask now, suppose I'm near a critical point. I know critical points are fixed points for the gradient flow because critical points are precisely where the gradient vanishes. So what do the dynamics look like near a critical point? So that depends, as you all know, that depends on what type of critical point you have. If the critical point is a minimum, then that critical point is attracting for the flow. So here, look at the first example. If you look at x squared plus y squared, so the graph of that is this paraboloid. It has a unique global minimum at 0. The negative gradient vector field is this minus the radial vector field, always points to the origin. So the flow lines always go towards the origin. They never quite get there, but in the limit as time goes to infinity, every point is taken to the origin. So no matter where you start, you will end up arbitrarily, you will quickly become arbitrarily close to the origin, and in the limit as time goes to infinity, you get sucked into the origin. So the origin is dynamically stable. So it attracts the flow. So now suppose instead that you had an index 1 critical point. So here, now look at the function x squared minus y squared. So the Hessian here is a 2 and then a minus 2. So there's one positive and one negative eigenvalue. This is a saddle point. And now the vector field is minus the gradient vector field is minus 2x, 2y. There's a simple way to know what the flow lines are of this vector field. Namely, if you think of the x squared minus y squared, this is the real part of a holomorphic function. So it's harmonic. The harmonic conjugate is 2xy. So the harmonic conjugate, its level sets are the flow lines of this function. So the flow lines of this vector field are actually where x times y is equal to a constant. So, so you see then, if you have these coordinate axes, then the flow lines all go, the only flow lines which are going into the origin are when y is equal to 0. So the x-axis is sucked into the origin, the y-axis is repelled off to infinity, and all the other flow lines are asymptotic to the y-axis. Okay, so there's only one flow line that goes into the origin. If you randomly pick a point, then with probability 1, it will not go into the origin. Okay, so there's a set of codimensions. So the critical point here is dynamically unstable. It's very, very unlikely that you would find it. Okay, so in order to find critical points like that by a variational argument, one would have to look at families of points. Okay, and then so this is where min-max arguments come in. Okay, so that's. Oh yeah, I should say one thing I always say is whenever I give a talk is please interrupt with questions and stop me whenever At this point, I'm probably not going too fast. But at some point, I may well. So stop me before that happens, or at least as soon as it happens. OK, so this is our background. So, right, so now let's look at the heat equation. So we've said that harmonic functions are the critical points here. So they're the fixed points for the flow. What does the heat equation, what does that flow look like near a harmonic function? Well, what's the simplest harmonic function? Just the constant function 0. So what happens if now I'm on a domain omega, and I look at an initial value, say arbitrary initial value, but I'm going to now restrict that my function always vanishes on the boundary of omega. The only harmonic function with boundary value 0 is the 0 function. Okay, so that's the critical point that we imagine this is probably going towards. So we'd like to prove that. So we already have shown that harmonic functions are minima, so they have index 0. So these should be attracting critical points. We'd like to prove that. That's what's going on now. So how would you prove that? Well, one way to distinguish the function that's 0 is it's the only function with 0 energy, and you're close to it when the energy is small. So let's show that no matter what u starts out as, the energy is limiting towards 0, and then we'll have shown that we're going to the 0 function. Okay, so let's do that here. So first, I want to do the divergence theorem shows that the energy, this is actually twice the energy, so the integral of grad u squared is minus u Laplace u. So just by taking the divergence of u grad u and using that u is 0 on the boundary. So now I take that and square it, and so I get the square of integral of grad u squared is now less than or equal to the first inequality is just Cauchy-Schwarz. I get a u squared Laplacian u squared. Now that using that u vanishes on the boundary, the Poincare inequality tells me that the integral of u squared is bounded by some constant times the integral of grad u squared. So this is just the ordinary Poincare inequality. So now I've got grad u squared on both sides, but I've got it squared on the left. So let me divide by that. And note that that's just the energy. And notice that the integral of Laplacian u squared, we showed that's basically that's minus the derivative of the energy. So here we have that twice the energy is less than or equal to minus some constant times the derivative of the energy. And this implies that the energy is exponentially decaying. In fact, it tells you it gives you a bound for the rate. The rate is related to the lowest Dirichlet eigenfunction of the domain. Okay, so you see exponential decay of the energy. This means that no matter what you start with, you are rapidly approaching the zero function. Okay, so the zero function is an attractor for the flow. Okay, well that's the zero function, but the heat equation is a linear equation. So the dynamics near any critical point are the same. You just subtract off the harmonic function and then do the heat equation here. So now suppose that you have some harmonic function on a domain, and now I look at some solution of the heat equation which is equal to it on the boundary. So W is the harmonic function, U solves the heat equation, and U and W are equal on the boundary, but not at the initial time. Right? Then I wouldn't move at all. So then U minus W also solves the heat equation, and it's 0 on the boundary for all time. And so the previous slide says that U minus W has exponential energy decay. In other words, U is decaying exponentially to W. So all harmonic functions are attractors for the flow. Okay, so this is supposed to have been a quick illustration of the ideas that we're looking at in a simple case that we're all comfortable with. So I'm going to go on, assuming that there are no questions, because I know that since I've virtually begged for questions, if there were some, somebody would have asked one. No? Okay. Okay, so energy of a curve. So now I'm going to look at a curve. So it's a closed, so it's on S1, so 0, 2 pi matches at the endpoints, into a Riemannian manifold with some Riemannian metric. It's always imagined the manifold is either Euclidean space or it's compact and without boundary. And then define the energy of the curve to be 1/2 this C prime squared, so that's just the derivative on S1. Okay, so now let's go ahead and compute the derivative of that energy, in other words, the first variation formula. So so now we want to take a path in the space of curves. So for functions, the space of functions was a linear space, so we just added another function to it. The tangent space to the space of curves is given by vector fields along the curve. So here I take some vector field V along the curve, that's the variation. And I'm going to consider this one parameter family of curves where and take the derivative of the energy and look at that at time 0. And when I do, I get this formula that it's the tangent vector dotted with this mixed derivative of the family of curves, integrating by parts to take that. I can interchange the order of S and T, just mixed partials commute here, and then I take that, move that S, so that's another derivative along the curve. So I get that it's minus the second derivative of the curve, now in the sense of Riemannian geometry, so think if you like grad gamma prime, grad C prime, dotted with the variation vector field. So this says that the gradient of the energy functional is just the second derivative along the curve. So critical points are solutions of C double prime equals 0. Those are called geodesics. So these, so geodesics are basically they are curves that are critical points for length, but with constant speed parameterizations here. Okay, so that's the energy functional on a curve. Critical points are geodesics. Okay, so now how would you produce a geodesic? So since they're critical points, one thing that you might do is try to find minimizers in some class. A reasonable way to do that, if you're looking for closed geodesics, is to fix a homotopy class and then try to minimize length in that homotopy class. Here we're saying free homotopy class that for technical reasons, basically, if you talk about a homotopy class, generally you want to fix a base point. But here we don't want to insist that all of these curves go through one fixed point, so we go to a free homotopy class where the base point is allowed to vary. Okay, so if you have a non-trivial free homotopy class, like here we have on a donut, so the class that wraps around the class of curves wrapping around the donut, here are 4 curves that are all homotopic. They're on the same free homotopy class. We can minimize length in this class of curves, or minimize energy in this class of curves, and it's easy to see that a minimizer exists, and it is a geodesic. Okay, so as long as the homotopy class is non-trivial in pi 1, the minimizer is also non-trivial. Okay, so it's very easy to find geodesics when the manifold has some non-trivial pi 1. Okay, so but how would you find? Oh, right. Okay, so and these are all minimizers. So by the way, from a dynamical point of view, if you imagine, so we'll see in a minute, there's an associated flow, like a curve shortening flow. If you started with a curve in one of these classes, it should be attracted to one of these geodesics, and that should be stable. If you perturb the curve a little bit, you should still end up at the same geodesic. Okay, so now, just like in the case of the harmonic functions, and in general for one of these, some sort of dynamical system, if you want to, the next thing to understand is what is the index of the critical point? Are you at a minimizer or possibly some saddle point? So here I just summarized the calculation of the second variation of energy of a curve and a surface. So you imagine, and looking at this slide, I can see that there's, of course, way too much writing on the slide, so that if you didn't already know it, it probably wouldn't be very helpful. But so just for the formulas, this is just the formula that you already know, which says that the second derivative of the energy along a curve can be given, and here we did a normal variation. So the variation V is a normal vector field to the curve. It's just given by the second derivative of the function times the function plus the curvature times the square of the function. So this, there's this is this Jacobi equation, the Jacobi operator in here. Okay, so, all right, so that's the second variation formula, and that tells us how to find minimizers. You'll notice that when the curvature is positive, then if you just stick the function phi in there, you always get something negative. So this is related to the fact that on the unit 2, the round 2 sphere, where the curvature is 1, there are no stable geodesics. None of the geodesics are actually minimizers for length, except for points. If you look, so the geodesics are the great circles, and those have index. So they're unstable critical points. So again, from the dynamical point of view, you would think it might be hard to find one. If you were to start off with a random curve, say nearby a great circle, it would likely not flow to a great circle. With probability 1, it would miss the great circle. Okay, so a geodesic is stable. So geodesics are critical points for the energy. If they pass the second derivative test, we'll say that they're stable. So roughly speaking, morally speaking, this means that stable geodesics are the ones that are local minima. That's not quite true for two reasons. One is, notice that I did a greater equal here instead of a greater. And the other is that it's, the space of curves is an infinite dimensional space, so you have to be careful about using things like, say, a Taylor series. Okay, so now, so I made a point of saying that it was easy to find geodesics when you had non-trivial pi 1. You just minimize in a free homotopy class. It's more difficult to find geodesics on the 2 sphere. Now, if you're actually on the round 2 sphere, there's an abundance of geodesics. Any great circle gives you one. So how would you find a geodesic? So take a 2 sphere, but now with a different metric. So here I've drawn on the right a 2 sphere that's supposed to be a surface in R3, and with the induced metric, so it's not round. And now how would you find a geodesic on this surface, or how would you show that a geodesic had to exist? So this is a variational argument due to Birkhoff from around 1917. And this is this idea of a sweep out. So here's how the problem is set up. So what we know that, let's think about it from the point of view of critical points. This geodesic is probably not going to be a minimizer. There's no reason for a minimizer to exist. It's most likely going to be a critical point with some index. So if you were to just randomly take some family of curves and, say, apply a flow to it or something like that, it would be very unlikely to end up at that one. Okay, sorry, not a family. Randomly take a single curve and apply the flow, it would be very unlikely to land up there. The way that you do that is you look at one-parameter families, and you know that most of them won't end up there, but one of them will. Okay, so that's the idea. So we want to look at a path in the space of curves. A path of curves, well, each curve is a map from S1, so a path of curves is a map on a cylinder. So it's S1, a map from S1 cross 0, 1 into M. And now we're going to have the top and bottom, so the beginning and ending points of the path of curves, we'd like those to just be point curves. So when you collapse the top and bottom of the cylinder, this means it's essentially a map from S2, topologically from S2 to S2. So we'll insist that map has degree 1. Okay, so this map from S2 to S2 has degree 1. And then, Now, along this this path, let's look at the maximum of the length. Okay, so there are places where you have points, and then the length is 0, but there are always places where the length is at least some fixed amount. Okay, and so now let's try to make that maximum as small as possible. So to do that, what you do is you pull this sweep out tight. You simultaneously shorten all the curves to make each curve as short as it can be while keeping the family continuous. Okay, so here you pull the sweep out tight. So you get some initial sweep out where many of the curves are long, and then as you tighten the sweep out, the longest curve in a tightened sweep out turns out to be a geodesic. Okay, and so this ends up being an index 1 geodesic. This is an example of the min-max argument. You're taking the maximum over the one-dimensional parameter space, the family of curves, and you're taking the minimum over the infinite dimensional space of all possible sweep-outs. So this should produce an index 1 critical point. That's exactly what it does in S2. Okay, so the best possible sweep-out of S2 is the one where you just intersect with parallel planes. The longest curve in that sweep-out is the equator, which has length 2 pi. All the other curves are shorter than that. Okay, and using the isoparametric inequality, it's not hard to see that if you have any sweep-out of S2, there's always a curve with length at least 2 pi. Namely, the isoparametric inequality on the sphere tells you that if you have a curve that divides the sphere into 2 regions of equal area, the length of that curve has to be at least 2 pi. So because this is a continuous family of curves, they'll always, with degree 1, there'll always be one that divides the area in half. There's always one with length at least 2 pi. Okay, so that's right. So so Birkhoff used this to prove the existence of a closed geodesic in S2 with any metric. Okay, so just a word about what was Birkhoff's. So this is Birkhoff's curve shortening process. Okay, so this is a critical point. What we're looking for is an index 1 critical point. So if you take any single curve and apply the flow, with probability 1, it will miss the critical point you're looking for. But now suppose you take a one-parameter family of curves. Each one of them, with probability 1, will miss it, but with probability 1, there will be one of them that hits it. Okay, so think, to go back to our picture, if you think of the flow, if we had this vector, the function x squared minus y squared, then we saw that only if you started literally on the y-axis would you end up at the origin. So if you take then a path of curves which starts above the y-axis, or sorry, a path of points starting above and ending below, and apply the flow to that, there will be one on the y-axis and that will get sucked into the critical point. It's the same sort of thing here. So we're taking this path for any individual one of them that's not going to hit there with probability 1, but one of them will. Okay, so how do we do the flow? So in 1917, Birkhoff did not have the curve shortening flow at his disposal. So he used a discrete version of it. So we'd like to do a discrete gradient flow. So what he did is he took his initial curve, which is this sort of rounded curve here, and I've drawn this in R2, where of course, there are no geodesics, non-trivial closed geodesics. So that might be a little bit misleading. Okay, so the initial curve, and then I mark 6 points on the curve. And now what I'm going to do is I'm going to look at, so I look, say, at the segment connecting to the point 2 and the point 4. I'm going to replace this segment by the shortest possible geodesic connecting those points. And then I'm going to replace the segment from 4 to 6, and then from 6 to 2. So I've replaced the even segments, and now I have a broken geodesic. So each part of this between the vertices is actually a minimizing geodesic, but the whole thing is not a smooth curve. It has these breaks. Then now I move the old odd points to the new configuration. Roughly speaking, if the point 1 was halfway between 2 and 6 on the original curve, I'd put 1 prime halfway between 2 and 6. And now I replace the odd segments by minimizing geodesics. So, and then I'm going to reparameterize the whole thing to constant speed at the end. Okay, so this is a discrete gradient flow on the path of the space of curves. So it has the same properties that a gradient flow does. It's continuous with respect to the curve that you have, and it decreases the energy along the flow. Okay, it's not a solution of the heat equation. It's like a discrete step process. So you just keep repeating this over and over again. And this was the method that Birkhoff used. By the way, the only fixed points to this are closed geodesics. And so here you'll see why we do the two replacements, even and odd. If I just did replacements on the even segments, the only fixed points would be geodesics that had possibly had breaks at all of the even points. Okay, so but if I do this double set of replacements, then because I hit in between, the only fixed points that are geodesics without any breaks. That's why you do the two-step process. By the way, this is in higher dimensions. This is very closely related to the Schwartz alternating method for solving PDEs. Okay, so energy, I could have just as easily looked at length of a curve. So geodesics are also critical points for that. The thing is that from the point of view of length, the parameterization doesn't figure in. The curve doesn't care what speed you traverse it at in terms of what its length is. Let's skip that. Okay, so that was a discrete gradient flow. So let's now go to the next topic, the gradient flow for length, for energy, or length, or well, in this case, for length. Okay, so this is called the curve shortening flow. So here I've drawn a curve shortening flow. So I have a closed curve, the blue curve in the plane. At each point, I look at the unit normal and I look at the geodesic curvature. And if the curvature, depending on the sign of the curvature, so I move in the direction of the unit normal with speed equal to the geodesic curvature. Negative speed just reverses direction. So here the red arrows indicate which direction the flow will be moving. You see that the flow tends to make the curve more convex. Where it's bowed in, it wants to push out, and vice versa. Okay, so this is the curve shortening flow. So what's the simplest example of the curve shortening flow? Just shrinking circles. So if you look at concentric circles, and if the rate, okay, so first of all, the circular shape will be preserved under the flow. So this is a geometric flow. So the flow itself is going to commute with isometries of space. So a rotation of space commutes with the flow. So then you'll see that the circular shape and the origin are going to be preserved under the flow. So you just get an ODE for the radius. If you solve that ODE for the radius and you set it up to, say, disappear at time 0, you see that the radius satisfies the radius at time t is the square root of minus 2t. So these concentrically shrinking circles flow smoothly up until t equals 0, and at t equals 0 you have a singularity. So this is called an extinction singularity. The flow disappears, becomes extinct. Okay, so this is an example of what's called a self-shrinker or self-similar solution for the flow. So this is more generally, it's an example of what's called a soliton when you have one of these evolution equations where the shape is preserved and just it evolves by some sort of rigid motion. So in that case, it was evolving by isometries, homothetic shrinkings. So solitons come up all over the place in evolution equations. So for instance, okay, so this is one, we'll see another in a minute. So if you have one that's moving by dilations, it's not hard to see that it must move by this formula in the second line. So the curve at time t is just the square root of minus t times the curve at time minus 1. And so again, and then of course the circles gave such an example. Abresch and Langer in 1986 classified the solutions to this, so the self-similar solutions to this flow, and they show that the round circle is the only embedded one. They're all convex, and they can be very interesting. Look, in the immersed case, they can be quite interesting. But if you ask for them to be simple, in other words, not to cross themselves, all you get are the circles. Okay, we'll see that the self-similar solutions play an important role in mean curvature flow. However, the classification is there's no corresponding classification. It appears to be impossible to give just a list of all of them. Okay, so what's the next soliton type solution? So Calabi discovered a curve in the plane that translates under the curve shortening flow, and she called the Grim Reaper. Okay, so this is a graph of the function t minus the log of sine of x. So here I've done one value. So you notice as t changes, all that happens is the graph translates vertically. So this is a solution of the curve shortening flow. and it's asymptotic to the vertical axis and the vertical axis translated by pi. One reason that this is, well, anyway, it's hard to say. I couldn't tell you for sure why I called it the Grim Reaper, but the maximum principle does tell you that if you had any other curve which lay somewhere in space here, it could never, and it was initially disjoint from one of these Grim Reapers, it could never touch the Grim Reaper. As the Grim Reaper translated north through space, it sort of wiped everything out, so that curve must have disappeared before the Grim Reaper reached it. So, okay, I don't know, I can spin a little story about that, I guess. Okay, so that's the Grim Reaper. So now, what's known about curve shortening flow? So in the plane, in 1986, Gage and Hamilton showed that if you had a simple closed convex curve in the plane, then it maintains all of those properties under the curve shortening flow. So it stays simple, stays convex, stays smooth. And you get an extinction singularity just like for the circle. So the flow is smooth up until some critical time and where it disappears. Moreover, if you were to look just before that critical time where the curve is very small and now magnify it back in space, the shape that you see is approximately round. So how is that proven? Well, they actually show that there's essentially the isoparametric ratio is monotone under the flow and approaches the optimal one of the circle. So in other words, if you look at the length squared versus area, that's optimized at the round circle, and that ratio improves under the flow and goes to the optimal one. So in particular, just by properties of convex geometry, that tells you that the in radius and out radius are converging to the same number, and so it's the shape is becoming round. Okay, so in 1987, Grayson proved what is probably still the most beautiful result in the subject, that if you take any simple closed curve, it eventually becomes convex under the curve shortening flow. Then once it becomes convex, Gage and Hamilton take over, and it becomes extinct in a round point. Okay, so and then there are generalizations to this to Riemannian manifolds. Notice in a manifold, where there are non-trivial closed geodesics, you don't necessarily know that it will become extinct. There's another possibility. If you're in a surface, it could approach a geodesic. Could exponentially approach a geodesic. That would be another possibility. Okay, so now here's an example. So this is an example called, it's supposed to look like a snake, I guess with a fat head in the middle. So this curve is a simple closed curve. It's obviously not convex. So by Grayson, this curve is going to become, eventually will become convex before it hits a singularity, and then disappear in a round point. Notice the curvature is wanting it to flow inward here. So it really it appears that it wants to intersect itself as these curves are flowing inward, but this part will unwind quickly enough so that you never get one of these singularities. All right, so this picture makes it appear very unlikely that Grayson's theorem could possibly be true. Okay, so there are, Grayson's original proof did not go this way. Hamilton found a very nice approach to proving Grayson's theorem. So it turns out that, so it turns out that in order to show Grayson's theorem, the biggest thing you need to worry about is ruling out that it's becoming very much like a Grim Reaper. Okay, so now one thing you notice about the Grim Reaper is the isoparametric ratio stinks. Okay, so if you were to look at a curve that's very far out on the Grim Reaper, you could have a short curve which divides the Grim Reaper into two parts of very large area, and yet the curve is short. So it's very much not like what you see on a sphere. So Hamilton's approach to showing Grayson's theorem is that he defines some isoparametric ratios that he shows improve during the flow. And these rule out the possibility of a Grim Reaper appearing. Okay, so Hamilton found two different isoparametric ratios that worked. So here's the first one. So if you have, the blue curve is supposed to be our curve in the plane that we're going to apply the curve shortening flow to. We divide, pick two numbers, A1 and A2, these are And now, so the A1 plus A2 is the total enclosed area. And now I look at a curve that divides it into, all possible curves that divide it into areas A1 and A2. And I look at the length of, the shortest length of those curves. And the quantity that I look at is this quantity I, where I look at L squared times 1 over A1 plus 1 over A2. Then Hamilton shows that as long as I is less than or equal to pi, I increases under the flow. So for the Grim Reaper, I is this quantity I is actually going to 0. So if you start off at some curve that is where it's positive, you're never going to arise. You will never get a small piece of a Grim Reaper appearing in the future. Okay, so this is used to rule out the Grim Reaper as a possible blowup. Okay, the second isoparametric ratio, isoparametric type quantity that works. So again, we have this closed curve. Now, again, you divide it into A1 and A2, areas A1 and A2, and then you draw a circle which encloses the same area as the curve, and you divide that up into A1 and A2. And you look at this arc which divides it into that area, which now has a length L0. So L0 is determined by A1 and A2. And you look at the ratio of L over L0. And then Hamilton shows that, again, this quantity improves under the flow. So again, this rules out Grim Reapers as potential blowups, because on a Grim Reaper, if you were to look again far away after it made its U-turn, then that curve is very short and the areas are quite large. Whereas on a circle, if you had a circle of large area, then that curve would have to be very long once the areas were large.
During the flow, you keep the ratio of A1 and A2 fixed because the total area is changing.
Yeah, so what you would do here is you would do like a renormalized flow. So you could take the flow and then just magnify it continuously in time to keep the enclosed area the same if you like, and then keep these guys fixed. Okay, so right, all right. So that's okay. So that's what I wanted. All I wanted to say about harmonic functions, the heat equation, and the geodesics and the curve shortening flow. So now we're going to step it up a little bit in terms of the functional, and we want to move to the area functional or volume functional. So now sigma 0 is a hypersurface in Euclidean space. N is the unit normal. And now I want to consider variations of that. So again, I'm thinking now of the space of surfaces, and the volume is a function on that space. I'd like to ask what the gradient of that function is. So first I have to talk about what it means to be a curve in the space of surfaces, a path in the space of surfaces. So that's this notion of a variation. A tangent vector to a surface is just given by a vector field along the surface. And so I define this one parameter family sigma s, which is given by, I take the point and then I move in the direction of the vector v of x by the amount s. So when s is equal to 0, I just recover the original surface, and as s varies, I get this family of surfaces, one parameter family of surfaces. So this is a curve in the space of surfaces. Now along this curve, compute the volume, and I want to take the derivative of that at s equals 0. So this is a directional derivative of the volume in the direction v. And the first variation formula gives you a formula for this. So a calculation shows this is just given by taking the divergence with respect to sigma 0 of that vector field v and integrating it up. Here's just a formula for the divergence. So if EI is an orthonormal frame for sigma 0, I differentiate v with respect to EI and dot it with EI. So that if sigma 0 was Rn, that would just be the ordinary notion of divergence. Okay, so this is the first variation formula. So this gives us what the gradient is. So this is not really suitable because it seems to depend on v. So we're going to, in a way that's not helpful. So we want to, just as with curves, we'd like to integrate by parts, basically, in order to make this formula look better. So that's what we'll do next. Okay, so now this is how we'll get the mean curvature. So the vector field v can be decomposed into the part tangent to sigma, which was called V tangential, and the part normal to sigma, which V perp. The divergence of the normal part, so V perp, again, this is a hypersurface, so I can just write V perp as being V inner product of the normal times the normal. And now I just compute what the divergence of that is. So when I differentiate this, I use the product rule to differentiate the term. I would get two terms. But when I differentiate V dot n, it's multiplied by an n. EI is tangential, so that drops out. So all I get is when EI hits n. So I get V dot n times, and then the divergence of n over there. So, but this is just the definition of the mean curvature. So the mean curvature is just defined to be the divergence of the normal vector field here. So if you like, this is minus the trace of the second fundamental form. So so now we have a formula that we like, right? Okay, so let's go to the next. So, oh, by the way, just to fix notation, the mean curvature doesn't come with a preferred sign. It's your convention what the sign is. With this convention, the mean curvature on the n sphere is n over r as opposed to minus n over r. Okay, so let's re-examine that first variation formula. So the divergence of the tangential part by Stokes' theorem, or the divergence theorem, that integrates to 0 if V is a compactly supported vector field. So all we see is the divergence of the normal part. Basically, that tangential part of the variation, that corresponds to reparametrizing the surface, moving it around. So it's not going to change things like the volume. So now the first variation formula now becomes that you get minus V dot H. This bold H is this, again, just to match up with conventions in the subject, bold H is minus the scalar H times n. Okay, so the gradient of the volume functional is exactly equal to the mean curvature. So critical points of the volume functional are ones where the mean curvature is 0, and those are called minimal surfaces. Here's an example. Here's a picture of a minimal surface. So this minimal surfaces arise physically as soap films. So the soap film acts to minimize assuming it's relatively homogeneous and gravity is essentially 0, it just wants to minimize its surface tension. So in other words, minimize its surface area. So you expect to get critical points for surface area. Here's an example of a soap film which is spanning this wire curve. So the wire curve has looks like this corkscrew with then this axis down the middle. So this is roughly like half of a helicoid. And here, if you, I don't know if you can see the reflection of the light reflecting off the soap film. Okay, so this is part of something like a helicoid. So that's one example of a minimal surface. Okay, so what does it mean to be a minimal surface? So from a PDE point of view, let's suppose that our surface is given as a graph of a function. In this case, so here the surface is given by a graph of a function u. So the surface lives in Rn plus 1. And it's given by the set of points, x comma u of x, where x is in Rn. Then the mean curvature of a graph is given by, you can work out, it's given by this formula. It's the divergence on Rn of grad u over the square root of 1 plus grad u squared. So to be minimal means that is 0. So this here's the minimal surface equation. This is a divergence form nonlinear PDE, well, quasi-linear PDE. And every minimal surface, minimal hypersurface, locally satisfies this equation. So if you, every smooth one, so if you take a point, then there's some neighborhood around that point where the entire neighborhood in the surface is a graph over the tangent plane at that point. So if you write that part of it as a graph, it would satisfy this PDE. So that's great locally. Of course, let me just mention one of the famous theorems in the subject. Globally, if you look for global solutions of this equation, it's much less interesting. So around 1916, Bernstein showed that if you have any minimal graph over all of R2, it actually has to be flat. So in other words, u is just an affine function. Okay, so globally, the minimal graph equation definitely does not describe all minimal surfaces. It just describes planes, but locally, it gives a good description. So I think that is time. So thank you.
Any questions or comments?
Mike.
I have a couple. So in your energy for harmonic functions,
Mm-hmm.
in a bounded domain, so we see that the finite amount of energy decays to the minimum finite. So what do you do what would you say if you start on an open domain where you have infinite energy? And you're still going to have some flow to something nicer.
Right.
Do you have any comments?
It depends a lot. Okay. Yeah. So if you have something, there are various conditions. So if you have you need some kind of control at infinity. Otherwise, you can't say anything. So for instance, suppose that you know that the initial energy is finite as measured against a Gaussian. Then you can get some kind of monotonicity properties along the flow. Right. Right, that's right. So otherwise, if you allow arbitrarily bad growth at infinity, then you can't say anything. In fact, the energy might even be increasing or something, you know. I mean, it's horribly infinite, but I don't know how you would say increasing, but the function may even be becoming worse.
Can you add these monotone quantities in the flows? I find mysterious. Can you suggest some intuition for Hamilton's quantities that are monotone under the curve shortening?
Not really. I mean, I don't know. Yeah, I mean, I think it's more just trial and error with those. With some of the quantities, I mean, that's people knew for quite a while that all you needed was some kind of quantity like that in order to prove Grayson's theorem. And it wasn't until almost 10 years after Grayson had proven it that Hamilton found quantities that worked under the flow. You get nice, so one of the things you notice is you get nice variation formulas for things like the lengths of geodesics under the flow. So, so in curve shortening flow, say the lengths of various curves, right, exactly, the cross things. So, and you get nice formulas for how the area changes under the flow. And so then exactly, you have a couple of formulas, and now and then you set up quantities trying to find one whose derivative involves those formulas. Yeah, unfortunately, there doesn't seem to be a good reason. And nothing like it is true in higher dimensions. So for instance, we'll see Grayson has an example of a dumbbell where a neck pinch singularity forms. So actually the number of components increases along the flow. So from the point of view of an isoparametric thing, that's terrible, because now you're dividing it with zero area into two different regions. So those quantities are definitely nothing like it in higher dimensions is monotone along the flow.